Now let's look at the other case that is made possible by the multivariate feature of the problem that we are studying here. So basically, previously we had those kind of straight or direct derivative in which you were doing derivative for multiple times repetitively with respect to only one variable, right? But here, because we have multiple variables, it's possible that you switch to another as you're doing derivative later, right? So here, this is what we call cross partial derivatives. That is to say, when we take the first partial derivative with respect to one variable for say x, and takes the second derivative with respect to another variable, for instance, y. So it usually is written as f partial on x then y, or f partial on y then x. Okay, and because of Young's theorem, we know that f partial on x then y is always equal to f partial on y then x. So basically the sequence of taking partial derivative doesn't change the value or result of the cross partial that you eventually work out. So here, let me show you the result here. So the first one, okay, cross partial derivatives. Okay, so for the cross partial derivative, now it's question 1c. So it is still the same function. And let's invoke the previous result. F partial on x equals to minus 4x plus 3y. F partial on y equals to 3x minus 16y. So now you are asked to do the cross. So you first take derivative with respect to x, and then you need to switch, right? So now in the second one, as you're taking partial derivative with respect to y, then in your eyes, now y is the only variable, and minus 4 times of x, the entire term is just a constant. So you're taking this derivative f partial on x with respect to y, so the result is just 3, right? The slope of this linear. And then fyx, so now you first taking partial derivative of this entire function with respect to y, and you have a new function which is 3x minus 16y, and now you are taking derivative with respect to x. So now what you're doing is on x, right? So the minus 16 times of y, the entire term is irrelevant, because now in your eyes, only x and x affiliated terms are your variable terms. So minus 16 times of y is a constant. So the derivative of 3x minus a constant is 3. And here, as you can see, fxy equals to f partial on yx. Okay, partial on yx. That's how I read it. All right, so this is the first one. Now let's look at the second one, which is the marginal utility. So previously, u equals to x1 square x2 to the power 6. And we found marginal utility partial on x1 is 2 times of x2 to the power 6. Marginal utility partial on x2 is 6 times of x1 square, x2 to the power 5. And now let's do the cross derivative. So for the first one, it is marginal utility on 1 first and then on 2. So as you're doing the second order derivative, you are taking the derivative of the first one, mu1, partial on 1, with respect to x2. So now in your eyes, x2 is the variable. So 2 times of x1 is a constant, multiplied by 6 times of x2 to the power of 6 minus 1. So the result is 12x1 by x2 to the power of 5. So let's look at the second one. So now it's mu21, partial on 2, then 1. So mu2, then you're taking the partial derivative with respect to 1. So the x1 term is the one that you recognize as variable. So in that case, 6 times of x2 to the power of 5 is constant. So you take the derivative of that, you keep it here, right? Because that's the k term that you are to keep unchanged as you are taking the partial derivative, right? So here in this case, k equals to 6 times of x to the power of 5. X is x1 and equal to 2. So here, its derivative is multiplied by 2, then multiplied by x, which is x1 to the power of 2 minus 1. So that is 6x2 to the power of 5 multiplied by 2x1, which is 6 by 2, 12, x1, x2 to the power of 5. And here, once again, the Young's theorem is verified. No matter what is the sequence, what the sequence is, the result is unaffected.